Thanks. All right, well, I hope everyone is doing well. So for today's talk, I'm going to introduce a research project that I'm currently working on, which for the purposes of this talk, I've titled Beyond Next Token Prediction in Code Large Language Models. So I think it's fair to say that today, next token prediction absolutely dominates text generation. So it's the essential training objective behind, I think, 95% of the models that we see today, if you account for stuff like BERT, etc. And even when you see new architectures spruce up like RWKV or Memba, they still rely on next token prediction at the core. And next token prediction can be broken down into two main components. So on one hand, you have the autoregressive generation part, which basically makes it so you predict one token at a time, and you predict all token XFT based on the past tokens. And this is used in transformers, but obviously we used to have this with RNNs as well. And even before that, we had unigram language models that would employ this autoregressive generation method. And then on the other side, you have subword tokenization. So tokenization takes many forms, but I think today we mostly mean tokenization based on an algorithm called BP that you may be familiar with. And the intuition behind BP is that it basically looks at the most co-occurring units of language and decides to form a whole vocabulary out of that. And so the intuition is that you end up with tokens. So short common words are as their own token, and longer, more complicated words end up as multiple subword tokens. So the idea for today is to kind of like identify what issues there are with this training objective and inference objective, and to try out some cool stuff and look at recent research to see how we can go beyond that. So the agenda for today looks a little bit like this. In the first part, we'll tackle autoregression, discuss the issues and recent improvements. Then we'll do the same with tokenization. And then I'll talk a little bit about promising directions that propose to go beyond this formulation. And at the end, I've had a cool announcements for you guys, so stay tuned. All right, so before I jump in the heart of the topic, I'm going to quickly introduce myself. So my name is Diego. I'm 22 years old, and I'm a research engineer at GEPU. So I used to study in Paris. I studied at a school called Epitech for 3 years, and then I moved to China in 2022 to pursue a master's in advanced computing at Tsinghua University. And so here I've included a few pictures of Beijing. Life is really cool in Beijing, and if you've got the chance to visit, you definitely should. And so during this time, I joined the knowledge engineering group, and about the same time I joined GEPU AI, and this is where I've been working ever since. So you may know GEPU. We've released quite a few models on Hugging Face, namely ChatGLM, CogView, CogAgents, etc. Recently we released Z1, which is our reasoning and deep research model. So it's available on Hugging Face. It's 32 billion parameters, and you should go check it out. And personally, I've been working with the team at CodeGX. So CodeGX is a code generation model that we released in 2022. And so from CodeGX, we built a product for developers. It has about 1 million users at the moment. And the main features, if you've used Cursor or Lovable, it's about the same. So we have code completion, code-based search, edge agent, etc. And all in all, with all these features combined, we process billions of tokens per day, which is not unheard of if you've got a successful, or at least a generative AI product with some users. But we're always looking to offer our service for the lowest possible cost, even offering the subscription for free if we're able to do that. And kind of like everybody else, we're always looking to serve the best model. And today, best usually means billions of parameters, and we're also looking to serve that at the lowest possible latency, and that's an important component. And to power all of that, you have to have large investments in GPU infrastructure, and that's why today we're motivated to explore the design space for code LLMs, in order to like uncover some performance improvement or speed improvements. And we feel that today going beyond NTP is a promising direction. So now I'm going to quickly touch on why this talk focuses specifically on code and not on natural language as a whole. So I think today code is treated very much the same as natural language in the training pipelines for state-of-the-art language models. But in my view, it's very different than natural language. First of all, it has structured by nature. You have like the syntactic structure of your programming language. And this means that usually when you're training or pre-training on code, you'll find that you have lower loss because code tends to have lower entropy. And that's due to the repetition, the syntax, etc. And another consequence of that is that the entropy distribution is also different. So what I mean by that is while you have some words in natural language that are harder to predict than others, the distribution of entropy is pretty smooth towards the text that you're training in most cases. While in code, you typically have some tokens which are really, really hard to predict, such as when starting a line or when you're naming a variable or a function. And then the rest of the structure or the implementation around that has lower entropy. And on top of that, coding has a lot of interesting tasks. So I think today we think LLMs and we think of them as chatbots kind of automatically. But we have a bunch of tasks in coding workflows, such as code completion or rewriting very large files where you have different needs, and sometimes latency and throughput is very important. So in my view, code is a great starting point to optimize this training objective. All right, so now we can move on to talking about autoregression in large language models. So I think it's fair to start by saying that autoregression is extremely efficient, and that's why it's dominated the field so far. So during training, you're making a prediction for every single token in your sequence, and this kind of like breaks apart from the training of RNNs, which we all know is very tedious and resource consuming. And theoretically, during inference, you're also able to leverage activation caching to reduce the amount of computation that takes place on your GPU. And so it's a very simple training paradigm to think about, but it's also very efficient. So while it's efficient and flexible, there is quite a few issues with next token prediction that are inherent to the training objective. So the first one that comes to mind is planning. So I've actually read an interesting study the other day by Huawei, who looked at training a transformer model on a synthetic task. So I've put an example of the task on the screen. And for humans, it's quite easy to solve. It's basically finding a path through a graph where you have a wrong turn that's possible. And so this wrong turn is considered as a hard sub-goal. And they find that the transformer autoregressive models can't really solve that, while other kinds of models can. So this is an example of a synthetic task that requires looking in advance to find the solution where models fail, but I think we have also examples from day-to-day lives. So for me, for example, when I ask an LM to write a program, sometimes it's going to omit certain imports that it's going to later use in the file. And this kind of means that when it started writing its response, it hadn't figured out exactly what it was trying to model. So that's interesting. And obviously people are aware of these limitations. So there have been quite a few works that are trying to tackle these different issues. So I think it's mostly geared towards the planning and the speed of inference. So the first one that comes to mind is speculative decoding. So speculative decoding is this idea that when you have some prior about what your answer is going to be, the answer of your LM is going to be, you can guide the model to decode faster by feeding multiple tokens at once. And I think people extended that to other objectives that look at augmenting the language modeling head with extra parameters and extra matrix multiply to basically teach the model to predict multiple tokens at every position. So token n+2, n+3, etc. Up to, I think, 4 tokens in the work by Meta. And this allows, obviously, to speed up inference. And it was used in DeepSeek training, but interestingly not in inference. And the way they justify this in the paper is they say that it helps densify the training signal, and it also helps the model plan its responses a little bit ahead, and it's also a way to do data augmentation, according to them. So now that we've touched on the issues for autoregressive LLMs, we can move on to tokenization. So tokenization is essentially what defines the model's view of the world. So it has big impacts on performance. So actually, we did a small experiment with a transformer, and we trained on Golang code. And we trained two different versions of this transformer. We trained one with a basic tokenizer from Hugging Face that you can see on the right-hand side of the screen. And the other one we used, we trained the model directly on the concrete syntax tree tokens, so the tokens that the Go compiler would see during compiling of a Go program. And after training, so it was a very small-scale experiment, as you can see. After training, we find that this model has superior performance on human eval, outputs code that compiles more often, and we did some tests on using it as a code completion tool, and it had some better feedback. So essentially, the reason why that is because current tokenizers kind of have arbitrary ways of representing language. And so the model during training has to basically learn these token-to-token transitions. And depending on how what tokenizer you're using, they may improve or hinder training. And we also find that tokenizers are very inefficient. So here I've plotted on a graph the distribution, or more the rate of occurrence of tokens per document for a bunch of models. And I've put this on a log scale. And what we find is that for GPT-4, about a quarter of the vocabulary basically never occurs, or at least in less than 1 out of 10,000 documents. And so while it's not so much an issue for performance, it's an issue when you're thinking of prompt injection or under-trained embeddings. And it also can slow down training and inference. So if you're thinking of training a single batch of Palm, so only the forward pass of Google's Palm, you'll find that you have about 2 terabytes of activations from the language modeling head just sitting in HBM memory, which is obviously pretty wasteful. And today we see models sometimes with up to 200,000 entries in their vocabulary. And just in general, tokenizers are quite clunky. So I think we're all familiar with the case of current models being unable to do string manipulation or to speak about the contents of their token. So I checked on my phone this morning, and the latest OpenAI model cannot say how many C's there are in cheeses. It's set 2. And one key aspect is, despite all this research, we still don't really understand the dynamics of tokenization. I'm thinking about a recent study by, I think, Hong Kong University that showed that, and they scaled tokenizer vocabulary up to 12.5 million, so using some tricks in order to not materialize this huge embedding matrix. And it seems to improve performance. So that means we're kind of far away from understanding the dynamics of that. So right now I've given a few examples as to why we could move a move beyond this next token prediction paradigm could be useful, but I think the most convincing argument is the speed wall that we're hitting right now. So if you have an H100, well, you're pretty lucky, but you get only about 3.5 terabytes per second of bandwidth. And if you compare that to the FP8 T-flops of the chips, that's about a 500 to 1 ratio. So for every byte that you move, you can do 500 operations on it before you start maxing out your compute and not be bandwidth bound. And current models, so at each forward pass, you have to load the entire model weights, except if miraculously your model happens to fit in the L1 cache. And you also have to move the key value cache to perform each decoding step. And so this is an immense, basically a wall on the speed of LLMs that is inherently due to the fact that we're decoding only one token per step. And so the idea for us is to search for an architecture that can address these issues and predict whole sequences in parallel instead of tokens that are one by one. And for that, I'm going to talk today about two interesting directions I think are worth pursuing. So on one side, you've got diffusion language models, and on the other, you've got tokenizer-free architectures. All right, so let's get into it. So starting with diffusion, I think we're all pretty familiar with the concept of diffusion. I'll lightly reintroduce it. So diffusion is defined as this two-step process in which you have a forward noising process that adds noise to your data samples iteratively, and then you have this reverse denoising process that does the inverse. And so usually this reverse denoising process is implemented as a parameterized function, so a transformer or a UNet model. And the forward noising process, so here we can look at the case of image generation. It usually looks like adding to each pixel in your image a small scaled Gaussian factor to add some noise to it. So diffusion is very cool because you essentially get a prediction for every single token in the image at every step. Sure, you need multiple steps in order to get the final image, but the idea is still interesting. And so diffusion has had quite great success in image generation. But then how do you apply diffusion to language models? So you can't really apply Gaussian noise to a token because it's essentially a continuous value versus a discrete value. And so you have to find other ways. So two implementations that we see often in what's called discrete diffusion models are to use masking or random perturbations. So here I've included two examples, and oftentimes the one with the mask is preferred is called absorbing state diffusion. And so we can see now how these models are usually trained and inferenced. So during training, so for this slide and the next one, I've actually taken the example of LADA, which is a diffusion model that was released in February 2025. And because there are many formulations for this discrete diffusion language modeling task, I've chose to stick with this one because it's one of the most scaled experiments, and they have some nice figures. So when you're training, you basically have a probability of masking to each token independently, and then you train on these noise sequences, and you make a prediction at each training step for all the masked tokens. And during fine-tuning, you're trying to adapt your model to this new distribution where you have a prompt, and obviously you don't want to mask out any tokens in the prompt. And so you adapt the model to represent this probability of the response given the prompt. Now during inference, the situation is a little different. So technically, at each step, you're making a prediction for all tokens, but you can't really rely on a single step to predict all the tokens in the sequence accurately. And so what you have to do is you have to discard most of the predictions that you make and keep only a subset. And this leads to very interesting paradigms, in my opinion. So the first one is that you can define a policy about which tokens to keep, so which predictions to keep, and which tokens to keep masked at each step of generation. And so that this leads to controllable generation. And the second one is that you can kind of modulate the number of steps to either make your inference faster or let the model refine its answer for longer. So if you're generating a sequence with n tokens and you choose a number of steps that's way smaller, you're going to be much faster than the autoregressive equivalent. And then if you choose a much bigger number of steps, you're going to have the inverse effect, which is really cool. Now, there are quite a few challenges of discrete diffusion language models that I think are interesting to work on at the moment. So essentially, the difference between continuous and discrete diffusion is that at each step during discrete diffusion, you're making jump between a mask token and a reveal token or accepting your prediction. So you basically have two choices for each token at each step, which is to either keep it masked or commit to your prediction. And once you commit to your prediction, there are some inference strategies which let you remask the token later or change the token later, but they may lead to the model failing to converge towards an answer. And so this process is much clunkier than the continuous approach of image diffusion models. And I was reading a paper the other day which had a really nice phrasing for it. So I've included two quotes from the paper in the slide. So they basically argue that those discrete diffusion models, they do kind of random jumps between masked and non-masked tokens. And it's essentially a Markov chain where you're discarding all the progress or all the computation that you made at each step if you choose to keep a token masked. And that's in contrast with the iterative refinement nature of continuous diffusion, where you're progressively changing, updating the value of your pixel till it converges to an image that's denoised. And so some people have looked at how to apply this continuous diffusion paradigm to language modeling. And so what they do is, instead of applying the perturbation in token space, they chose to apply it in latent space, so at the word embedding level. And then they can apply the same Gaussian noise that you use and that you see in continuous diffusion language models. And then at the output of the model, they have the loss, which is based on a rounding step. So they technically take the embedding and map it back to token space. So this idea of working with latent embedding spaces instead of tokens leads me to my next point, which is to introduce tokenizer-free architectures. So when I was at Tsinghua, I actually did my thesis on tokenization. And the idea was trying to develop a better tokenizer, first of all, one that modeled the semantics of language better than BP did, and also one that could scale to larger tokens, maybe tokens that were composed of multiple words in order to speed up inference. And so what I realized along the way is that the best tokenizer is no tokenizer at all, because the tokenizer is, to me, the last bit of clunkiness in an otherwise very optimized architecture, like end-to-end architecture, which is a transformer. And so there's a series of models which take this approach, so tokenizer-free models, and they don't work directly with a fixed set of tokens or a fixed vocabulary. And instead, they operate on what's called patches, which are groups of bytes or characters, and there are quite a few rules on how you can construct those patches. So some approaches decide to split using predefined rules, such as splitting on spaces to obtain patches that correspond to words. Other works, like Megabyte, which is a pretty famous paper from Meta, choose fixed size patches. And more recently, we've seen techniques such as entropy-based patching, where you look at the entropy of the next byte to determine your patch boundary. And this leads me to talk about a work that I find really interesting that was released recently, which is the byte latent transformer by Meta. And a few things that I found interesting in this paper. So they basically use an encoder which applies this entropy-based patching, and then they use the latent transformers, which works over latent patch representations, and then you have a decoder that handles the mapping back to a byte space. And there are three takeaways which I feel are very interesting. First of all, they show that you can trade speed for a minor decrease in quality by increasing your patch size. So if you let your patch size be 8 or higher, you're basically processing more characters or more bytes per token or per patch than a typical transformer. Secondly, they show that their approach scales better than transformers, and I think it's a really valuable insight that by having this more end-to-end architecture, you can improve the convergence during training. And finally, it kind of brings the idea, because you're segmenting patch around entropy, is that you can have dynamic allocation of compute, wherein sentences that are, or sequences that are hard to predict require more forward passes, while really easy sequences require fewer forward passes. And so it's a great departure from the current transformer architecture. And so this idea that you can take bytes and pull them together into a higher level representation, so go from characters up to the word representation, kind of begs the question, why stop here? So this is where stuff like hierarchical transformers come in. And they basically work around the idea that you can take your byte sequence or your character sequence and build word representation from pooling the bytes together, and then do the same thing for higher level representation. So take words and build sentence embeddings out of that, up to paragraph embeddings. That's the theoretical understanding, at least. And what this paper achieves is a reduction in the number of elements that are involved in the attention computation, which is, I think, a really interesting contribution, especially when we see how architecture today are mainly limited by this factor. And they also show, like the authors previously, that their approach scales better than the basic transformer, which is cool. So what are the goals for us at JPU? So what we really want to land is a comprehensive ablation study into all the works that have tried to go beyond this next token prediction objective, and kind of provide a comparison with scaling laws, convergence trend, the speed during training and inference, etc. So we hope to land a technical report in June and integrate different cool architectures like diffusion, language modeling, or tokenizer free. So you can check this out on TI2CAD when it comes out. And yeah, in conclusion, the core idea behind this talk is that for some tasks, so here we focus on code, NTP is just too slow because of the KV cache, because of the autoregressive decoding, and you have two promising ways to tackle this. So diffusion, you can make it faster when you're using less denoising steps. Then you have tokens. This leads usually to better planning ability, and it doesn't necessarily use fixed flops per token. And tokenizer free enables you to more flexibly represent language, and it can also be a way to trade speed for performance. And I want to close by reiterating that this is targeted at specific use case, which is code. And the main reason behind that is that we believe there are no silver bullets in model design. So you're going to have architectures that do better at certain tasks, and you have needs that are different for each task. So yeah, this is the main takeaway. And right before I close, I just want to make a quick announcement. So we're opening a company in July here in Paris, which is called Superconvergence. We're going to be working on AI for coding. So if anything that I've talked about today interests you, please feel free to reach me out at this address that I put on screen. And yeah, we're going to be hiring for research engineers and software engineers to build super cool research and product around AI for coding. So yeah, stay tuned. And one last thing is, if you have any feedback, I don't normally give talks like these. So if you feel I could have mentioned something that you feel was lacking from the presentation, or just any feedback in general, it would help me a lot to improve if you just submit this quick feedback form. So that's all. I'm just going to leave you with my references. Thank you.
Wow.